Today we will learn about the category creation procedure of an end section joint in PDMS. So we will start from a basic square box and we will build it continuously. Okay. So first of all we have to go to Paragon, and in Paragon we have to click here and we have to go to steelwork. Okay. So after that we will go here. This is a normal section, a structural section, as you can see, STC, STAC, and after that we will click on create and we will click on category and then for joints. Okay, this is the category for joints. We'll click here and we will click on OK. So as you can see that a new joint category has been created. Okay, so just for reference we will click here and we will just change the name as end section joint, then we will type STIFF for stiffeners. Okay, then we will click on rename all and apply. So now the name is correct here. Okay, so now what we will do, we will just turn our P point on and our axis on. Okay, so this is our general configuration, and now we will go to component, and under component, under the generate type, we'll go here, and from here we will click on JOIN, as this will be the category of a joint. Okay, so after that we will click on apply. So now what we will do, first of all we will go here in dataset and we will define the plate length and plate width. Okay, so let's do that. So we will type here plate width and we will give here as the D key as the PWID. Okay, and this will be definitely a design parameter. Okay, this will definitely be a design parameter and the value will be real and the default value will correlate to parameter number 1. Okay, so we will type here param1 and after that we will click on apply. Okay, so this is our plate width. Okay, so now here we have to change it to plate width also. So we will just type here plate width. Okay, and we will click on apply. After that we will type here plate length and we will click on new because now it has been defined. Okay, so now we will go to here this PNG file, and currently we are building this SBP1 kind of thing. Okay, this one. So as you can see that in our case both this length and this width are same, but for different purposes we will define it differently. Okay, so after that we have to define the plate thickness value. Okay, this is the plate thickness value, we have to define that. So for that we will go here and we will type here plate thickness and we will click on new. So now the plate width, plate length and plate thickness values have been defined. Okay, so after that we will go here and we will check the next value that we have to define is the center bolt to bolt distance. Okay, this is the center bolt to bolt distance and this is the web bolt to bolt distance, or you can say this is the flange bolt to bolt distance and this is the web bolt to bolt distance. Okay, so we have to define those bolt to bolt distances. So for that we have to type flange bolt to bolt distance, click on new. Now we will go here and change it to web. Okay, web bolt to bolt distance, and we again will click on new. Okay, so now the flange bolt to bolt distance and the web bolt to bolt distances have been defined. Okay, so now we will go here and again we have to define one last parameter, that is the bolt offset in the direction of the flange. Okay, in the direction of the I flange. This is the bolt offset, this is the end offset of the bolt. Okay, so we have to define this parameter also. So for that we will go to here in Paragon and we will just go here and we will type here end, just for reference. You can name it whatever you want, but in our case we will name it as end bolt to bolt distance. Okay, so now it has been defined also, and again if we click here we can see that all of these parameters have been defined. So now what we have to do, we have to find this nib values. Okay, these are the nib values, these are the nib values of the stiffeners. So in our case I think you can define two different nib values, like this one as nib 1 and this one as nib 2, but in our case for simplicity we will define it as a single value, that is only nib. So for that we have to define this stiffener height, this stiffener thickness and the stiffener nib. Okay, so let's define these three values now. So we will go here and we will type here as stiffener height first of all. Okay, so it is stiffener height. Now we will click on new and now we will click here as stiffener nib. We will click on new and the last value of this thickness of stiffener will be stiffener thickness. So all these three values of stiffeners have been defined. Okay, so we have to define now the bolt holes. Okay, we have to define these bolt holes, bolt hole diameters. Okay, So for that we will go here and we will type bold dia, and after that we will click on new. So the bold dia parameter has been created, and after that we have to define the shim plate. As you can see, these are the shim plate. Okay, so here also, as you can see, that this is a square shim plate. You can definitely define two different parameters, one for shim length and one for shim width, but for simplicity purposes, again, I will define only one parameter, that is shim plate length, and another one parameter for this thickness value. Okay, so again we go to Paragon and we will define shim plate or shim length, I should say shim length. We will click on new, and again we will change it to shim thickness. Okay, and now we will click on new. Okay, so almost all these parameters have been defined. So now what we will do, we will go to here category. Okay, and now it's time for us to put these values. Okay, so as you can see, both this value of plate width and plate length, both of these values are 480 in our case. This is an ISMB kind of thing. This is in column kind of section of 300. Both the web distance and the flange distance are 300, as you can see, almost 300. So this plate length and plate width value both are 480. Okay, so we'll go here and we will type here 480, and here as plate width also 480. So again we will type a 20 plate thickness just for reference, and now we will click here as the flange bolt to bolt distance. We have to check here the flange bolt to bolt distance here is 145. Okay, so again we will define here as 145. Now we will go here, that is the web bolt to bolt distance. Okay, so what is the web bolt to bolt distance? This is this distance, and this is 390. Okay, so again we will go here and we will type here as 390. Now what is the end bolt to bolt distance? As you can see, this is 45. Okay, so again we will go to Paragon and we will type here 45. And what is the stiffener height? Let's say a stiffener height of 200 mm. And what is the stiffener nib? Let's say a stiffener nib of 25 mm. What is the stiffener thickness? Let's say a stiffener thickness of 10 mm. What is the bold dia? The bold dia, I think it is defined here, that is the 37.5. It is the bold dia here, so we'll just define that, that is 37.5. And after that we will go to shim length and shim thickness. Let's say a shim length of 50 mm and the shim thickness will be 10 thick plate for shim plate. Okay, so all these parameters have been defined correctly. Okay, so now we will go to dataset. As you can see, we have to define all these dataset values. So for that, this is the first plate width value. So we will just click here new, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so all the values are defined here. So now we have to define it one by one. Okay, so we'll click here plate length. We will just copy it and we have to go to dataset and just refer it here, plate length, and the D key will be, I think, PLEN. We will change this number to 2 and we will change this to param 2. Okay, we will change this to param 2 and we will click on apply. We will just change this to plate width actually, because this was the first parameter. So PWID, this will be 1 and this will be param 1. Okay, so we'll click on apply. Again we will go here, this will be plate length and the D key will be PLEN. The definition will be design parameter, definitely. The number will be 2. The type will be real and the default value will be parameter 2. As you can see, the parameter 2 corresponds to length. Okay, so again we will click on apply. Then the value will be plate thickness. So we will just copy from here and we will type here plate thickness. Okay, plate thickness. So here the D key will be PTHK. The definition will be design parameter and the number will be 3. Okay, the type will be real and the default parameter will be parameter 3. So again we will click on apply, and after that we will click here. The fourth parameter will be flange bolt to bolt distance. Okay, and you can give the D key as FBTB, and this will be our design parameter number 4, and we will change the type to real and we will refer the parameter 4 value here. Okay, so now it has been referred. Now we will copy it and we will define the web bolt to bolt distance. Okay, so this is our web bolt to bolt distance and you can define here as WBTB, and this will be our next design parameter and the number will be 5. Type will be real and the default value will be parameter 5. We'll click on apply. After that we have to define end bolt to bolt distance. So just type end bolt to bolt distance and the D key will be EBTB. Okay, and the definition will be design parameter. The number will be, I think, 6. Yeah, and the type will be real and the default value will be parameter 6. Now we have to define the stiffener height. So we will type stiffener height here, and the DQ will be SHEI. The definition will be design parameter, and the number will be 7. The type will be real, and the default value will be parameter 7. Okay, we will copy the stiffener value from here for referring for the dataset values. So here it will be stiffener nib, okay, and the DQ will be S nib, and the definition will be again design parameter, and the value will be I think 8. Yeah, the type will be real, and the default value will be parameter 8, param 8. Okay, so now the next value will be stiffener thickness. So just type it here as stiffener thickness, and the DQ will be STHK, design parameter number 9, type will be real, and the default value will be parameter 9. We will click on apply. The next value will be bolt diameter. Okay, so just type bolt dia here, and the DQ will be B dia. Definition will be design parameter number 10, I guess. Yeah, number 10 it will be. Number 10, type will be real, and the default value will be parameter 10. Okay, so click on apply. After that, we have to define the shim length. Okay, so just define shim length. We will use the DQ of SLEN, change it to design parameter number 11. We will change the type to real, and we will define parameter 11 here as our default value. We'll click on apply. We'll just copy the shim from here, and we will define the last dataset value, that is the shim thickness. Okay, STHK. So definition will be design parameter, number will be 12, type will be real, and the default value will be parameter 12. Okay, I think this S key has already been defined, this D key. I think this is defined for stiffener thickness, I guess. Yeah. Let's change the stiffener thickness to FTHK, and change this shim thickness to STHK. Yeah, now it is perfect. So our data set has been completely defined. Okay, so now we will create a single geometry, and we will check whether it is working or not, and then we will build upon it. Okay, so for that, first of all, we have to go to positive geometry set. Oh, again, we have missed one thing, that is we have to define the attached element data set point. Okay, so what is attached element data set point? As you all know that that I have already discussed earlier in my other episodes, that for an end section joint there is no owning section type, but definitely there is one attaching section. So we have to define that attached section. Okay, so for this case, so we will click on new. Okay, so we will click on new, and we will type here as asec. Okay, so we will type here attaching section. Okay, attaching section. Yeah, attaching section, and we have to set here as set attached element. Okay, we have set here set attached element. So we will click on apply. As you can see, it is applied. So for reference, we will give one a default spec reference value. Okay, so for that we will go to design, and we will just take the specification reference of this HEB 300. Okay, so this is the specification reference of this beam. So we'll just copy it, and we will just paste here in the reference tab. Okay, so after that we'll click on copy. So as you can see, the default value has been taken here. Okay, so now we'll just save it. Okay, so now it has been completely defined. So now we will go to positive geometry. Okay, so for first of all, we will create a extrusion. Okay, solid extrusion or extrusion. The z axis will be our sectional axis. Okay, so we will create the joint on the xy plane. Okay, so our first axis will be x, and our second axis, first axis will be definitely y, or it will be vice versa, it doesn't matter. So in my case, I will take y as the first axis and x as the second axis. So I will change this to x. Okay, and the height will be this plate thickness value, that is RPRO PTHK. Okay, RPRO means reference properties. So this is RPRO PTHK. PTHK is the D key that has been defined corresponding to the plate thickness value under our data set. Okay, so for that, after that, we will click on apply. Okay, so we'll just click on modify points, and as you already know that there will be 4 points for a square element. So we will just copy it 3 times, and after that we will define the values. Okay, so now, as you know, our first axis is y and our second axis is x. Okay, in this case, so if you click on modify points, this will correspond to all the y values, and this second column will correspond to all the x values. Okay, so we will put the values like that also. So for that, in the y direction, we will suppose put RPRO PWID divided by 2. Okay, yeah, like that. So this will be on the y direction. Okay, this will be on the y direction, and it will rotate in the clockwise direction like this. Okay, so like this. So the second value again will be RPRO PWID by 2. The third value will be negative RPRO PWI by 2, and the fourth value will be negative RPRO PWI by 2. So all the four values are defined. So now we have to define what? We have to define the x variations. Okay. So let us guess this, the first value comes in this coordinate. Okay. In this zone of this coordinate system, the y and minus x zone. So the first value will be -1. Okay. So we'll just copy it from here and we'll paste it here, and we will change this PWID to PLEN to refer the length properties. Okay. So I have just copied it here. So the P length value has been defined. So as I have already mentioned, it will go in the clockwise direction. So here the second value will be positive. Okay. So we will click on here. As you can see, the second value has been defined. So the third value will again be positive as it will fall under this zone, -yx zone. So just paste it here. Yeah. And we will just copy it to mention the last point of this extrusion set. Okay. So as you can see, this total extrusion has been defined. Okay, perfectly. So now this plane, this xy plane is the starting position of our section. Okay, so we have to create this joint above this one. Okay, so suppose if you create a section starting from this location, okay, and after that if you create an end section joint, so the end section joint should be at the end of this end of this section. Okay, that means the end of this joint should not be here but should end at this location. Okay, so we have to shift it upwards by this thickness value. Okay, so we'll just copy it here and we'll paste it on the z coordinate. Okay, we'll just copy it and it will be minus value, as I have changed the axis. So according to right hand rule, it will be changed. Okay, the direction. Now it is going upwards. Okay, so now it has been perfectly defined. So just for a reference, we will refer this category in an already defined joint specification, and we will check whether it is working perfectly or not. Okay, so for that case, we have to go here. We have to go in our in this one. Okay, so just for reference, we will name it something like Q name, and we'll put here 1 just for reference, 1. Okay, or we can give you a variable because it will be a variable stiffener kind of thing. Yeah, variable, it will do. Okay, so now we'll just copy this name of this category reference and we'll paste under the spec component. Under this spec component, this is our intersection joint specification that we have already created in the earlier videos. So we'll just paste the category reference here. Okay, so now as you can see that the category reference has been perfectly pasted under the specification component of the spec end section joints. Okay, so now what we will do, we will go to design. Okay, and after that we will do one small gate work and save work. And now first of all, we have to check that the primary node creation is on and the primary node storage area has been set perfectly. So after that, we will go to modify joints and specification, and we will click on that end of the attached section. And now in this case, this end. After that, we will click here, and as you can see that the end section joint stiffness variation is shown here. Okay, if you click on properties, as you can see, lots of properties have been shown. These are all set by us as design properties. Okay, so all the design properties have been shown. So if you click apply, as you can see that it has been perfectly created. Okay, so now just open the axis, and now if I click on look south. Okay, so if I click on look south and if I click on F8, now as you can see that this is the end of the section. This is the end of the section. Let me click on this thing so that you can identify it better. As you can see now, this is the end of the section. This point is the end of the section. So the joint has been created in the perfect position. Okay, but what is the difference? The section will end on the top of this plate. Okay, but now the section is going through the plate and it is ending on its natural position. So for that we will create a negative. Okay, to cut the section. Okay, so just click on F9 for opening this toolbar. So what we will do, we will now go to Paragon and we will define one negative geometry set. Okay, negative geometry set here is the difference between a negative geometry under a positive geometry and a negative geometry set. The negative geometry set is a more powerful tool and it's specifically used while creating categories or templates or something like that, and mainly sectional things like sectional joints or in-section joints like that. And it has different various powerful properties that a normal negative element under a positive geometry cannot be we cannot define all those things. Okay, there. So first of all, here we will create one negative solid box. Okay, we'll create one negative solid box, and the length and y, x length and y length we have to define. Okay, so what will be the x length and y length? We will write here a par 1. Okay, we will write here a par 1, and we will write here a par 2. What is a par 1 and what is a par 2? I will definitely tell you. First let me define it, then I will tell. And here we will write RPRO PTHK, I guess that is the plate thickness, RPRO PTHK. Okay, so now click on apply. As you can see, now it has been created, but we have to move it upwards, I think, because the center is absolutely at the origin. So we will just click here and we'll move it upward, I guess. Yeah, now as you can see that the negative has been perfectly created. So now we will click here, remove from attached. Yeah, now it is perfect. So what is a par 1 and what is a par 2? Okay, so if I go here the design, okay, so if I click here and if I type here as QCatRef, so I will get the category of the section. Okay, so I will just go here and paste here on Paragon. Okay, so as you can see that this is the category, and if I click on modify category, then the category of the section will be displayed here like this. So now this is our attached section as we have defined here as the data set. Okay, this is our default value. Just to show these properties, even if you define 0 as the default value, it will definitely take the default values from your design once you attach end section joint to a section. Okay, now this is our attaching section. So anything starting from A, and if you write PAR after that, so A par, it will correspond to all these values of the attaching section. Like a par 1 will correspond to the depth, a par 2 will correspond to the width, a par 3 will correspond to the wave thickness, like that. Okay, so all these values will correspond to, like a par from a par 1 to a par 12. Okay, so if you write a par and if you put it like that, like this, okay, so a par 1, a par 2, this will correspond to that number of that number values. Okay, that numbered values, like a par 1 for depth, a par 2 for width, like that. Okay, so now the negative has been defined perfectly. Okay, so now I have defined the nav value as remove from attached, so it will remove from attached, and then definitely I think okay, so remove from attached will do here. The plate need not be removed from that area, so we'll click on apply. Okay, so after that we will click here save, and we will perform one small get work and save work to check the changes. We'll just remove it, and I think we have to delete it and create it once, I guess, because only that will affect, I guess. Yeah, only that will affect. So for that, just let me delete this p node first. Okay, so let me delete this p node and we'll create one p node again. So modify joint specification, we'll click at this end and we'll now click here. Okay, so now if you click here F8, as you can see that, yeah, as you can see that this section is no longer coming to the bottom of the plate. Okay, it is ending at the top of the plate. As you can see, it is ending at the top of the plate because we have defined that negative. Okay, and we have set the nav value as removed from attached. Okay, so this is the attached section, so it is only removing whatever it is removing from only the attached section. If you click on F8, as you can see that nothing has been removed from this plate. Okay, but only from the attaching section. Okay, so now it has been perfectly defined. So now what we will do, we will define all our stiffeners. Okay, just measure it once as if it were 300 by 300, just for a cross check. And this is the measure distance start and this is the measure distance end. So it is approximately 300 by 300 anyway. So now what we will do, we'll go here in Paragon, and for now we have to create all these stiffeners things. Okay, first of all we will create extrusion. We'll go here and we will click on extrusion. Okay, so now we will create this extrusion on the ZY plane. Okay, this will be our extrusion plane, and it will be extruded along the x-axis. So our first axis here will be Z and our second axis here will be Y. Okay, and our stiffener thickness value will be put under the height value, so that will be RPRO FTHK. Okay, so we will write here as RPRO FTHK. We'll click on apply, and now we will click on modify, and as we know that a stiffener will corresponding to a 1 point, 2 point, 3 point, 4 point and 5 point. Okay, so we will click here 4 more points, 4, 5. Okay, so now all the 5 points have been defined. Okay, so as I have already told earlier that our first axis here is Z and our second axis here is Y. So if you click on modify points, these values will correspond to all the values under the Z axis, and these values will correspond to all the values under x-axis, or sorry, under y-axis I guess, because our next our next axis is y. Okay, and our extrusion direction will be along x-axis. Okay, so for that we have defined our stiffener height already, that so we have to take care of that. So our first value will be definitely 0 0. So our second value will be PRO SHEI. Okay, and the y direction will be again 0. So now we will click here as RPRO SHEI, we will put here RPRO SHEI, and we will put here as RPRO SNIB, as this will be the nib value. Okay, as you can see that it has been displayed now. So after that what we will do, we will define our third value. So what will be our third value? Third value will be this length. Okay, this length. Third value will be this length. This length will be our third value. So what will be the expression of that? That will be RPRO PLEN, or P width it can be. It is a symmetrical structure, but we have to check it further. So RPRO PLEN minus of 0.5 into A par 1, I guess. A par 1. Yeah. And this will be cut from here. Copy. This will be pasted here. Okay. And we have to here also put a 0.5. Yeah, perfectly. So now this length will be again RPRO SNIB. Okay, this length will be RPRO SNIB, and now we will copy it and we will paste it here, RPRO SNIB. This will be 0, but the y value will be this one. Yeah, this will be the y value. Yeah, perfect. Now it has been perfectly defined. So what we have to do, we have to shift it towards the z axis, because as if you put F8, as you can see, it is going underward. Okay, so we have to shift it upward. So for that we will put a z coordinate here. So our z coordinate will be RPRO PTHK, that is the plate thickness value. And as the axes have changed, so we'll just check which axis is corresponding to the height. Yeah, then definitely it will be x-axis, I guess. Yeah, it is definitely the x-axis. Okay. Yeah, now it is perfect. Okay, so now as you can see that there is a certain deflection along the axis, and it is not positioned centrally. Okay, so we have to position it centrally. So for that we will just copy this extrusion value and we will just put it here like this. We'll put a minus sign for the direction and we'll click on apply. Okay, so as you can see now it has moved to a central position, the stiffener. Okay, so now what we have to do, we have to move the stiffener outwards. Okay, so for that case we will just put a y coordinate value. So what will be our y coordinate value? Definitely it will be 0.5 into A par third bracket 1 space third bracket. Okay, so you can see now this is shifted to the correct position. Okay, so now if I go to this picture, you can see this is our central stiffness. So now we will just save it here once, apply, save it here, and we will just do a quick get work to check whether our orientations are correct or not. Okay, so what we'll do, we'll just remove it and we'll just add it again. Okay, so as you can see, I think our orientation is not right. Okay, this thing will be along this flange thicknesses, and all the three stiffness will be along the flange. Okay, so for that case we will just go to Paragon and we will move it at the outward locations. Okay, so for that we will not need this z value. So again now it is perfect, so we will just shift it outwards. Okay, so for that we will just put here 0.5 A part 2, 0.5 A part 2 minus RPRO FTHK, I think. Now click on apply, and as you can see it has moved towards the end of the section. Okay, now we will just copy it for once, and we will give a negative sign here, and we will delete this one as it will not be required because it will be shifted on the other direction. Okay, so now it has been perfectly positioned. Okay, so now what we will do, we will copy all the stiffness to the other direction. So for that we will just copy it, and as you know that this z direction will be same and it will be mirrored. Okay, so this y will be minus y as it will be mirrored, and so just click on apply, and we will just copy it, and we will change the axis to minus y and click on apply. Okay, so all these things are perfectly positioned. So just for a check, we will again do a quick get work and a quick save work. We'll just remove it and re-add it. Okay, so now as you can see that this has been perfectly positioned here. So now what we will do, we will create the other stiffness on the other directions, and that will do our work. Okay, so for that we will just copy this one again, and now it will be rotated on this direction. Okay, so we will put anything, x or minus x. Okay, both direction we have to create. So if you put on X, you can see that it has been created perfectly. So again, we will just copy it and we will just put here -X for the mirrored stiffener. And as you can see, it has been perfectly mirrored. So again, we will just copy it and we will just put a negative sign here and we will delete this RPRO FTHK value and we will just click on apply. And as you can see, it has been again perfectly positioned, and we'll just copy it and mirror it once again by putting here X and clicking on apply, click on apply. And now all the stiffeners have been perfectly positioned. So now we have to create the intermediate stiffeners also. So for that we will click on copy, and I think we have to put 0.5 into RPRO FTHK. The directions we will see, I think it will be a negative direction. So just put negative here and check whether it is correct or not. Yeah, I think it is perfectly correct. Just click on look -X, I guess. And if you go here, as you can see, it is perfectly middle. Okay, it is perfectly positioned. So we will click here and we'll copy it and we will change the axis to -X. Okay, so again we will click on apply, and as you can see, the intermediate stiffeners have already been copied perfectly. Okay, so we will click on apply and save it. Okay, so now what we have to do, we have to create the shim plates. Okay, so for that again we will go here, and for shim plates we will create a box for easier references. You can definitely create extrusions and you can do like that, but I think if I create extrusion also, it will be easier because then I can refer it to P point. Yeah, so for that we have to define the first P points here. Okay, so for that we will go to our point set. Okay, and we will create a Cartesian P point which can move on any Cartesian plane. We will give the number here as 1, and our axis direction will be, I guess, x-axis. X-axis will do. So we will just click here apply, and we will give the bolt hole distances here. Okay, so we will give the bolt hole distances. So for that, this first thing will be referred in the x-axis, in the negative in the positive x-axis I can take as RPRO, weight bolt to bolt distance, I guess. So RPRO BTB. So if I click here 1, definitely it will be like 0.5. Now it is perfectly positioned. Now we have to defer it by RPRO FBTB. Okay, so we'll just copy it here and we will just paste it here, and we will change it from W to F, and we will click on apply. As you can see, this point is perfectly positioned. We'll just copy it, change it to 2 and change the Y value. Okay, so now we will click on apply. This value has been created perfectly. So now we will copy it, change it to 3 and change the X value. We'll click on apply. We will copy it again, change it to 4, change the Y value sign and click on apply. Okay, so now we will click on save, and all the 4 bolt holes have been defined. We have to define the last 4 bolt holes that are the end holes. Okay, this portions will be allotted for those bolt holes. So for that we will click on here and we will copy it and we will put it 5, and the Y distance values will be changed. Okay, so the Y distance values will be changed. So it will be like RPRO PLEN. Okay, RPRO PLEN minus 0.5 RPRO PLEN minus EBTB. Okay, 0.5 RPRO PLEN minus RPRO EBTB. So like that. So now the 5 has been positioned correctly. So we will copy it and we will just put 6 here. Okay, so now we will change the Y value and we will click on apply. So the 6 has been positioned. We will copy the 6. We will again change the number and we will change the X value, the direction of the X value definitely, and we will again copy it and change this and the direction of the Y value, I guess. So delete it and click on apply, and 8 is been positioned perfectly. Okay, so now it is our time to create the shim plate. Okay, so for that we will create extrusion. Okay, in the YX plane. Okay, in the YX plane, and for that we have to put here the shim thickness, that is RPRO STHK if I'm not wrong. Okay, so we will click on apply, and now we will go to modify and we will copy it 3 times because it will be a square plate, and this will be our Y direction, this will be our X direction. Okay, as this is our first axis is Y and our second axis is X. So we'll just go here and we will refer it as 0.5 RPRO SLEN. Okay, so 0.5 RPRO SLEN. Perfect. So it is along the Y axis, as I have already told you, this is along the y-axis. Okay, so now the next one will be negative, okay, because it will rotate in a clockwise direction. So just put it here as minus. Then again the next one will be negative, so just copy it and paste it here. Okay, so the last one will definitely be positive. Okay, so just paste it here. Now it is termed for the x values. So the first two x values will be positive because those are coming under the positive x-axis. The last two x values will definitely be negative because those are coming under negative x-axis. Okay, so as you can see that this shim plate has been created perfectly. Okay, so what we have to do, we have to just lift this shim plate up. Okay, this shim plate is created under it. Okay, so for that we will just have to move it up. So we will just type here, I guess, z coordinate rpro sthk plus rpro pthk, and as we have changed the y and x axis from x and y, so the z direction will be negative. If I click here apply, as you can see the shim plate is perfectly positioned here on top of this plate, as you can see. Okay, so now what we will do, we will just give our x axis, okay, axis value. So from here we will type p1. Okay, we will type p1 here. Okay, so we have to type the y axis values actually, so just type x here and apply, and we have to go to point set, I guess. So we have to change all these directions to y, apply, and if I go to positive geometry set, now if I change this y to p1, as you can see this will be shifted to p1. Okay, so we have to update this point set directions first. So we'll just change it to y from x, and we'll change it to y from x, changing it currently y, and the last one will be changed to y. Yeah, so now what we'll do, we will go here and we will copy this shim plate. Okay, and we will just change the p point references of that. Okay, so by that we will just do it as many times as this is required, so it will take a few seconds. So just copy it and change the p point again to p5, copy it again, change it to p6. I guess it will be continued to till p8, so two more extrusions to be created, p7, and the last one as p8. Now all the extrusions have been created and positioned perfectly. Okay, so now it is time for us to create all the bolt holes. So for that we have to go to our negative geometry set and we have to define our negative cylinders. Okay, so for that we have to go to negative solid cylinder, and we have to give our height as some height like 100, and our b dia will be bolt dia, that is rpro b dia. So we will write rpro b dia. Okay, so we will click on apply, and as you can see the axis will be z because it will be along z axis. So as you can see it is created perfectly. Okay, it has been created perfectly. So we will just middle it for better negative activities. Yeah, now it has been perfectly middled also. So now what we will do, we will again go to point set and we will just copy all these points. So it will be 9 and the axis will be z. We'll copy this to value, change the axis to z, copy this to 11, change the axis to z, copy this to 12, change the axis to z, copy this to 13, change the axis to z, copy this to 14, change the axis to z again. Now it's done for the 15 and z, and the last one as 16 and z. Okay, so all the new p points have been defined. So now we have to refer all these negative cylinders to through the correct p point. Okay, so our starting p point will be p9, I guess. So we will just click on apply. So it has been perfectly positioned. Now we will just copy it and we will change the p point reference values. Okay, for the axis. So it will be p10, copy it again, it will be p11, I think it will be up to some p16 or 15, something like that. So again we will change it to p12, and now p13, p14, p15 and p16, the last one. Now what we have to do, we have to remove it from attached an item. Okay, attached an item. You can also remove it from item, it will not matter much, but for accuracy I will remove it from attached an item. So I will now change all the corresponding nav values from default to remove from attached an item, and we will just applying it all together. Remove from attached an item and apply, remove from attached an item and apply, and lastly this is the last one, that is remove from attached an item and apply. Okay, so now we will just save it. Now it has been perfectly saved. So now what we'll do, we'll again go to design, do a quick get work and save work. Yeah, and we'll just remove it and we'll again add it. Okay, so now as you can see all these things have been perfectly defined. Okay, as you can see all these things have been perfectly defined. So you can just go to click here the pjoy, and you can go to modify and properties to change all these parameters. So just if you click here 550 and 550, as you can see, and if you click on apply, as you can see, it has been changed. Okay, so after that you can just change the shim plate length to 75 and apply. This has been applied. Now you have to change the bolt to bolt distances, and the end offset you can change. So in bolt to bolt distance, if you change it to from 45 to say 60, like that. And now if you change this web bolt to bolt distance from 390 to like 420 or something like that, so again click on apply. As you can see, all the values have been changed perfectly. Okay, all the values have been changed perfectly here. All the corresponding values have been changed perfectly here. So if you just go here, you can see that there is again a plate here actually. Okay, so you can again create this plate by extrusion also. We can just create this plate again, no matter. So just go to Paragon, and I think the plate will be along this direction, if I'm not wrong. Yeah, this plate will be along this direction. So for that, what we have to do, we have to again go to the category of this section. Okay, so just for that, go to QCatref and just click on this category, because we have to check which parameter of this section corresponds to the flange thickness value, because that we will need actually to define that plate correctly, the length of the plate correctly. Okay, so the flange thickness value corresponding to A par 4 in our case. Okay, A par 4, as you can see, this is the flange thickness value, A par 4. So now what we will do, we will just refer the stiffener thickness value for that plate. So we'll go to positive geometry set first, and we will create an extrusion here first of all. Okay, so that extrusion will be along the zx plane. Okay, so we'll click here Z, and we will write here X, and the thickness will be as per the stiffener thicknesses. Okay, so it will be RPRO, I guess FTHK, the stiffener thickness. Okay, so we'll click on apply. Again we will go to modify points, we'll go here, and we will copy it thrice. Okay, so the height will be like just like the stiffener height. Okay, so the first Z value will be, definitely the Z will be 0, but the X will be something else. Okay, so the X will be, I think it will be negative 0.5 into A par 1. It will be A par 1 or 2, because it is a symmetrical section actually in our case. So if you take any unsymmetrical section, then you can just check it and cross check it, like if it is A par 1 or 2, because in case of a symmetrical section, it is a bit difficult to understand it. I can definitely open the category of the section and cross check it from there, but it will take some more time. So let's just do it like this. So it will be 0.5 A par 1 definitely, plus I have to take care of the flange thickness. Okay, so I will write here as A par 4. So it will be the first value. Okay, so definitely the second value will be having the same X value, but the Z will be changed. The Z will be changed to RPRO stiffener height, that is SHEI. Okay, so this is the Z value. As you can see, this is the Z value, and this is the gap. This gap has been created for the section flange. Okay, this gap has been created for the section flange thickness. Yeah, perfect. Now what we will do, again we will copy this thing, we'll paste it here, and we'll just copy it, we'll paste it here, we'll delete this sign, and we'll put a minus sign for the reversal of signs. And now we'll just copy it here and paste it here. Okay, so now it has been perfectly defined. Now all we have to do is we have to shift it upwards by the amount of plate thickness. As you can see, it has been created just above the origin, so we have to lift it upwards. So it will be done by putting here RPRO PTHK. Okay, I think it will be put under y coordinate if I'm not wrong. RPRO PTHK, sorry, it will be put under which coordinate? Z, I think. Z will do. Z is not doing also. Yeah, so it will be under X coordinate. You can just do it by trial and error. It is nothing very difficult. Now as you can see that it is in perfectly positioned. Okay, so now what we have to do, we have to shift it towards this axis. Okay, it's towards this axis. So for that we have to define as minus A par 2, I think, and divided by 2. Yeah, like that. So it has been shifted perfectly. Okay, perfect at the end. Okay, so now if you see here in the design, as you can see that there are small cuts. Okay, these are the small cuts. So for defining those cuts, we have to define a negative F radius. Okay, in the points F radius or P radius statement. Okay, so this is our first point. So if you define minus 10, as you can see that this negative F radius has been created. Okay, so again in our last point, if you put here as -10, as you can see, this has been created perfectly. Okay, so now what we'll do, we'll just copy it and reverse the direction. So again we'll copy it and we'll just reverse the direction, and we'll just add its extrusion length because it is not positioned centrally. Okay, so after that, if I click on apply, you can see that this sign will be negative, I think. Yeah, now it has been positioned perfectly. So one last thing that we have to do is we have to define all this f radius value that I've missed somehow. So if you go here, I think all these first values will be -10. Yeah, perfectly. So it will be just a mechanical thing to change all these values to -10 to define all these f radiuses. So modify points -10, extrusion modify points -10. Again go to modify points -10. Okay, modify points -10, modify points -10, modify points -10 here also. Just let me complete it quickly because it is a repetitive work as I have overlooked it earlier. So just let me finish it quickly. Yeah, now every f radius or p radius, you can say, has been defined correctly. Okay, so now if you just perform a small save work, and if you go to design and do one small get work and save work, and just remove this p node for once and re-edit, you can see all these things have been created perfectly. These f radiuses are also shown here like that. So this is how you create a category of an end section joint. Okay, this is the general procedure. You can definitely add more and more details if you like, but this is generally how you do create a end section joint category. Okay, thank you for this episode, and in the next episode we will discuss about creation of a category of a section to section joint. Okay, single section to section joint. Bye.